Greetings everyone, and welcome back to our online lecture series for CHE 2300. Today I'm going to pick back up talking about heat transfer, specifically talking about heat transfer through pipe walls, which you'll see will become very relevant when we start to talk about different heat transfer equipment. So in the following scenario, we have a hot fluid with a temperature T sub H. Flows through a pipe that has an inner and outer radius of R sub I and R sub O respectively. In this example, we are going to assume heat flow only in the radial direction, right? So only in the R direction. So if I were to describe the general heat transfer process in the scenario I'm showing, what I have is I have heat convection from this hot fluid to the inner surface of my pipe that now has a temperature of T sub I. Next, I have heat conduction through the pipe radius to an outer surface T sub O. That is followed by some convection away from the surface based on the fact that we have some cold fluid out here, T sub C. So we might imagine having hot water inside this pipe and cooler air on the outside of the pipe. Okay, so mathematically, how do we describe heat transfer in this particular scenario? The first thing we're going to do is describe heat conduction through the pipe wall. We can describe heat conduction using Fourier's law of heat conduction in cylindrical coordinates. So here is our heat flux in the radial direction. The heat flux is equal to the heat flow in the radial direction divided by the area through which that heat transfer occurs. All of that is equal to the negative of the thermal conductivity of the material multiplied by the temperature gradient. Again, because we are in cylindrical coordinates, we have dt dr. We are only worried about heat transfer in the radial direction. At steady state, we know that our heat flow is constant, and we can describe the area of our cylinder by 2 pi RL. So if I plug in 2 pi RL, that is equal to negative K dt dr. Now I'm going to integrate both sides of this equation. So I move the dr over to the other side, and I take the integral from the inner radius to the outer radius. On the other side of my equation, I'm going to assume that my material has a constant thermal conductivity. And I'm going to take the integral from T sub I to T sub O of dt. When I perform that operation, I get the heat flow in the R direction is equal to 2 pi L times K times the temperature difference between the inner and outer surface of the pipe. All of that divided by the natural log of the ratio of the outer and inner radius of the pipe. So again, this equation describes heat conduction through the pipe wall. We can take that equation, write it in a bit of a more familiar form to what we saw in lecture 18, where heat flow is equal to the thermal conductivity, and we had it multiplied by some area. Here, we're going to define a new term. This is log mean area, and we'll discuss that here in a second, multiplied by the difference between the inner and outer surface of our pipe, divided by the difference between the outer and inner radius of our pipe. Our log mean area term here is defined as 2 pi L multiplied by the difference between the outer and inner radius of the pipe, divided by the natural log of the ratio of those two quantities. We can write that in an even simpler form if we define a log mean radius. Whoops. Okay, so 2 pi L log mean radius, where our log mean radius is equal to the difference between the outer and inner radius divided by the natural log of the ratio of those two quantities. So the question becomes, why log mean area slash radius, right? Why do we use a log mean area here instead of simply some area? If you remember from lecture 18, when we had heat conduction through a wall, right? As I progress through the thickness of this wall, if the height of that wall is H, the length of that wall is L. As I move through the thickness of my wall, the area through which heat transfer, or the cross-sectional area, does not change. It remains H sub L throughout the entire thickness of that wall. Hopefully, as you can see or appreciate, if we look at this picture of our pipe, as we move right from the inner surface of our pipe towards the outer wall of our pipe, the area through which heat transfer is occurring is changing because the radius of my pipe is changing, right? And the area through which heat transfer occurs is 2 pi RL. This number right here, this radius, is changing as I move from the inner radius to the outer radius. So I need some term that defines that heat transfer, right? Taking into account that I don't have a constant area of heat transfer when I have heat transfer through this pipe wall. And so in that case, what you find is we'll define some log mean term, right? These log mean terms are common, and you'll see next year in mass transfer that they will also pop up, right? So in this case, we have a log mean area or a log mean radius. and that is used to account for the fact that the area through which heat transfer occurs in this pipe changes as a function of the radius of the pipe. Keeping our colors consistent, we have heat convection to the pipe wall, and we'll talk about heat convection in more detail in the next lecture. So heat convection to the pipe wall, we have a convective heat transfer coefficient that is multiplied by the area. In this case, that is the area of the inner surface of the pipe, and that is multiplied by our temperature driving force, which is the hot fluid in the cooler inner wall of the pipe. So here we have convection to pipe inner surface. We can write the same for the outer surface, so the heat flow is equal to some convective heat transfer coefficient multiplied by the outer radius of the pipe. And then our temperature driving force from hot to cold, so T of the outer surface minus T of our cold fluid. This would be our convection from term. Proceeding as before, we can take all of those terms, add them together, and we get a final equation which describes the heat flow through that pipe. In the numerator, we have the temperature difference between the hot fluid and the cold fluid, and that is divided by 1 over convective heat transfer coefficient for the hot fluid, area of the inner surface of the pipe, plus our conduction through the pipe, so difference in the outer and inner radius, divided by the thermal conductivity times the log mean area. Let's keep our colors consistent here. Since this is conduction, and then convection from the outer pipe surface, which has our convective heat transfer coefficient on the outer surface multiplied by the area of the outer surface of the pipe. Okay, so hopefully you can see that this equation is set up exactly the same as the equation in lecture 18, where we had a temperature difference divided by the sum of our thermal resistances in the system. Where these two are our convection terms, and that is our conduction term. And so again, we have conduction through the pipe wall, and we have convection to the inner surface of the pipe wall from the hot fluid, and then from the outer surface of the hotter pipe wall to the colder fluid that is surrounding it. Okay, much like last time, we can also define this in terms of an overall heat transfer coefficient. So these are convective heat transfer coefficients. but we can define an overall heat transfer coefficient, our big U. We saw last class period, in lecture 18, that our overall heat transfer coefficient took this form. And again, the question pops up, which A, or area of heat flow, do we use? It says, as A changes with radius, the overall heat transfer changes depending on the selection of what area we use. That is, we need to define both an overall heat transfer coefficient based on the area of the outside of the pipe and an overall heat transfer coefficient based on the inner area of the pipe. And you would have to be given or told which one of those to calculate. Okay, so let's go over an example to see if hopefully any of that made sense. In the following example, let me fill that in. Okay, in the following example, what we have is saturated steam on the inside of our pipe, and it's housed in a pipe of unknown length. The steel pipe is surrounded by air at 70 degrees Fahrenheit. The inside and outside radius of the pipe are 5 and 6 inches respectively, and the thermal conductivity of the steel is 24.8 BTUs per foot hour degrees Fahrenheit. We are also given the convective heat transfer coefficient on the inside of the pipe, or the hot side of the pipe, and we are given the convective heat transfer coefficient on the cold side of the pipe. We're told here that the air has a temperature of 70 degrees Fahrenheit, and our saturated steam has a temperature of 220 degrees Fahrenheit. The problem asks us, what is the heat loss per length of pipe? The equation we can start with is our heat flow equation. Right, this is going to give us our heat loss. So that's going to be our delta T divided by the sum of our thermal resistances in the system, which we just saw was 1 over the convective heat transfer coefficient of the hot fluid on the inside of the pipe times the area plus our conduction through the pipe wall. And then finally, convection away from the hot pipe to the colder surrounding air. And that is based off the outer surface area of the pipe. And then our temperature difference here is going to be the temperature difference between the steam and the air. But this particular problem asks us to calculate the heat loss per length of pipe. We're told that we have a steel pipe of unknown length. So what we're going to do is we're going to take our equation here, and we are going to divide it by the length of our pipe. And when we do that, I'm going to do a bit of rearranging as well. I guess we've been doing capital R's here. Capital R. Capital R-O. Again, all I've done is take this equation right here and divide it by L. I've also plugged in 2 pi RIL here, 2 pi ROL here. I've plugged in my terms for my log mean area as well.